Test, 1, 2, 3.
What you need?
Nothing. That's not a habit.
All right, what did I do for that?
Sorry about that, folks. Apparently our audio visual guy was struggling with one of the cameras we have here. I want to introduce to you what we're doing so that it has some relevance. Right now you're seeing the machine, or you were seeing the machine laying up this layup that we have right here, which we produced previous to this. It's laying it up really fast. We have 4,000 inch per minute adds and 3,000 inch per minute cuts. So it's a very high performance layup in that regard. And also it's a very challenging layup. You can see there's lots and lots of exposed toe ends everywhere. And there's some pretty short toes, and there's some smaller gaps down in the middle there. The point of today's demonstration is to promote our AFP 4.0 philosophy for doing layups and fiber placement cells. Today's demonstration is going to be primarily focused on the inspection side. You'll see the machine doing layups, and then when it's done with the layup, the automated inspection system approves the layer and then allows the machine to proceed automatically. Apparently we've just finished the layup, so you saw this layup occurring. It's now done. We've done the real-time inspections done, and now we're moving on to the visual inspection side. So I guess so far the demonstration's gone really well and that the layup is really good. Let's go look at the layup. All right, so hopefully you're seeing what I see here, but a really high quality layup. All the toes are in the part. Every toe's been inspected. In fact, the ply fill's been assured. At this point, we have inspected all of the toe ends and every toe-to-toe interface in the laminate. So we're going to go back now to the inspection PC and look what we got as far as the inspection goes. And meanwhile, while we're doing that, the laser vision unit up there is going to start inspecting the visual inspection. We're trying to eliminate the need for that secondary inspection. And so here we go. I'll show you how it works. Oh, okay, thank you.
So it has a ribbon tape.
Okay, I'm apparently live now and on our inspection system. So I'm going to zoom out. The very last ply we did of that part looks like this. The part starts in the middle and then builds its way out. And then from the outside and builds its way in. You already saw that earlier. I won't belabor it too much. Okay, so what we're looking at here is the yellow is the ply as it was supposed to be laid, and the pink barrels are the locations of the toes as measured by the real-time inspection system we call RIPIT. The strategy here is the machine will lay a layer like this, very much like this, and then if the inspection system says it's good, and I'm going to pull up a different one here. If the inspection system says it's good, then it allows it to automatically go on to the next ply. So this ply was before the one we just showed you. What would have happened is this ply would have been laid, RIPIT would have real-time measured these. At the end of building this ply, it would either have been approved or not. Every one of these was approved, so that's a really good sign that we have a good layup. Once it's approved, it would then move automatically to this ply and create it. So that's what you guys saw. Maybe we'll go back and replay some of that or relay it if we want later. So now we're doing the visual inspection system, and I'm going to check and see with my team and see if it's going. Okay, I got a thumbs up. So there's a lot of toe ends there. It's going to take a while to process these, but I think, are they coming in?
Yep, click on them.
On that one. Oh, there we go. Okay, so there's a toe. I'm going to zoom right on in here, and what you can see. Oh, okay, there we go. So it's getting a little coaching from the team that wrote this software. So the yellow, the maroon barrels or purple barrels are from our real-time automated inspection system, and the white barrels are from the visual inspection system. You can see that they compare very well for the most part, and then we'll check some of the areas where they're not quite the same and kind of figure out why. Let's see, refresh. Where'd the image go?
One of these guys. Yeah, just click anyone.
Okay. Nice. Okay.
So now you got
Yeah,
the
go
whole
ahead.
shebang.
Okay, so it sounds like I'm back live here. I had to get a little coaching. So the data's kind of slowly populating, and that's the way it does with the visual system. It's a great system. It's certified, and it is used in factories in the world today. But we think that Ripit's even maybe a little bit better. And we're going to show you why. Or I guess you saw why, because it's fast. The plies are inspected within 5 seconds of completion. And by comparison, this one here is taking a little bit longer to do. So we can zoom in. We can see we're getting images of the ply. We're getting data filtering in from the vision system. And we can go in and look. And you can see that we're getting really good correlation between Ripit and the vision system. The vision system is certified. Ripit is in the process of being certified. The vision system is somewhat slower. The Ripit system is basically instantaneous. So the measurement data we get is not perfect on either system. What we see is, in this case here, is a good one where the vision system had a failure where it measured, actually took a measurement, it expected to see some toe here. The real toe actually landed about here, and Ripit was more accurate in that case. So you do see discrepancies between the two. The goal with these systems is to provide an accuracy of measurement if 2 sigma plus or minus 60 thou for vision and 2 sigma plus or minus 100 thou for Ripit. We've been able to reliably show that, and that's sort of where the state of the art is of this system. We're going to take a brief pause while this finishes, and we'll be right back in, say, 2 minutes. Okay, it's fun looking at this inspection data. It came out fine, but what I want to do is go ahead and kick off another layup so you can see it. The layups again are done at an extremely high rate, and this is meant to be a very challenging part for AFP. And we're demonstrating how well the machine can do such a hard thing. All the adds and cuts are 3,000 inches per minute. Half of the adds are more like 4,000 inches per minute. Okay, so I heard the machine beep, so I think it's about to start, and I'll shut up and let Matt...
Oh, never mind.
All right, I'm back with you here. I wanted to show you that, but basically what you're seeing is the video of the machine, live feed video of the machine, and below that is the feed rate of the surface speed of the machine. So you'll see the spiking going up to 4,000 inches per minute at times. You'll see it slowing down to 3,000 inches per minute. That's the point of the graph below to show you the performance of the equipment. Okay, that's it. Okay, I wanted to jump in here real quick. As we're doing these layups, you'll notice it'll finish, apply, and pause. During that pause, that's when the automatic inspection system is making its final calcs. Once it does, if it's approving the ply, it'll send a signal to the CNC to continue on. Also, you're going to see our speeds are starting to come down. As the pieces get really short and the gaps get small, the machine automatically slows down to maintain reliability. Okay, we'll go back to the action. Okay, I'm jumping in one more time. So just so you know, we've been running continuously here since 1 minute after the hour. I got almost 10 minutes after the hour, so just 9 minutes. In that time, we've placed over 1,250 individual strips of tow. We're only running 4 lanes. You do that to preserve, to get cycles on lanes without spending, you know, it costs us about $12,000 a full head. So it's nice to only have the 4 lanes. It's a little more economical to do that way. But we are getting the actuations on the tows. That's the equivalent of doing 5,000 tows on a 16 tow head. And since we've done 2 of these bunt cakes for you, that's the equivalent of 20,000 tows. The average fiber place part in the Boeing factory is somewhere around 150,000 tows or so. So you can see we're doing significant portions of events right here in this live demo. You're seeing the reliability of the equipment and the sheer speed of the equipment. I don't think there's any AFP equipment out there going this fast, and here we're doing it for you live.
Low battery warning.
Okay, so some statistics for you. We did 2 bunt cakes. That's equivalent to 3,000 strips of tows laid by only 4 lanes. Those 4 lanes are producing floor-to-floor rate of over 37 pounds an hour, almost 40 pounds an hour of fully inspected fiber placed tow with only 4 lanes. This is a 16-lane AFP head. We only use the 4 lanes because we want to get the actuations on the lanes to demonstrate reliability, and we can't afford to run 16 bobbins at a time. Just the material's $45 a pound, my price, so we opted to limit the number of lanes, but to get the actuations up, we have short strips of tow. And even with those little tiny short strips of tow, what you saw was floor to floor, almost 40 pounds an hour. Folks, this is your one last chance to look at the layup. We did, like I said, the 2 bunk takes. You can see the average toe is really short. Here's the smallest toes, and then they get a little bigger, and a little bigger, and a little bigger, bigger. But the longest toes are really only about this long. We've still got 37-point-something pounds per hour out of only 4 lanes of a 16-toe head. So that just shows the potential of this AFP 4.0 system. It improves the quality of the part is extremely high. The reliability of the equipment and process is extremely high. The rate at which we put this together, the production rate is very high, and the utilization of the equipment is nearly perfect with AFP 4.0. And we recommend that you come see us and contact us often so that we can help you operate one of these things, which is really a money press for you. And I think we can have that.